3, 2, 1, here we go. Okay, so now we have the correct values for this B. So we have this now. Inference line of supposed to be RA. That's correct. Okay, we have RB. So now you should be able to guess by now, because now it's playing with the determinate structure. So for, let's say, you can now for RC use sigma Fy equal to 0, right? It becomes very simple now. So RC is therefore going to be equal to 1 minus RA minus RB, right? Because now we have RA, we have RB, so we can use the basic sigma Fy equal to 0. Okay, so likewise, I'm going to give you the inference line right away, because this is too straightforward. Okay. All right. So I think, if the inference line of RA looks like that, what you see, the inference line of RC should look somewhat like this. Okay, this better be 0 at that location, and that is 1. Correct, for sure, that is 0. Here is minus 0, 1. Here is 0.14. Here is 0.375, and here is 0.672. This is straightforward, so I don't suppose you have any question. Now, the interesting thing is about the next one, because it's about the VD. Okay, D is the point, midpoint between support B and C. So in order to get this, now remember, now we have the structure with all the reactions. But in order to get the remaining stuff correctly, now I don't think you recall this, but the first step when we try to study the inference line, we use the free body diagram, and this time we have no choice but to go back and use the free body diagram. Okay, so let's say this is A, this is B. You cut the free body diagram at D, you get this shear. Okay, but remember, you have the unit load. The first free body diagram is when the unit load here is lurking around on it. Okay, and the free body diagram remains the same, but you have to move the unit load across your structure. So there will be the time when the unit load moves further away from point D, and your free body diagram can look like this, right? The first case is when the unit load is between 0 and 6 meters. Okay, or I can say 0 x 6. Okay, this is your free body diagram. All right, and then this is your second free body diagram when your unit load is between 6 and 9 meters. Of course, the distance we refer to the distance count from support A on the left. Okay, so here is 6. Now, so it's straightforward enough. Your VD here is simply equal to RA plus RB minus 1. But here, VD is just RA plus oops, sorry, I said A, but I wrote B. You like that? RA plus RB. Okay? So from here, we have our influence line. Okay? Oops, I'm out of space. Okay, good. So now the I don't need to straight. Okay, right. So from this, I would have something like let's map where my point B is. Okay, we're gonna have something like this. Okay. Wow. Okay, looks beautiful enough. From the equation, the value that we have at B has to be 0, right? When the unit load is on B, how can you have shear at C? Here is 0.031. Here is minus 0.14. So around this. This is minus 0.375. This is 0.625. Here is 0.328. Okay, so you can say that this is VD equals RA. Again, can't believe that. RA plus RB minus 1. And this is simply RA plus RB. Okay, and here is the influence line of VD. Okay, any question? Now, last one, MD, right? Similarly, you know by now that what all you have to do is to cut the free body diagram. So now you have A and B. Okay. And your moment right here is where you're going to take the moment, right? MD. And the first free body diagram is when you have the unit load on it, which means that this is your free body diagram when you are. Can I actually copy this? Let's see. I'm gonna fail again, maybe. Yep. You know, when you see that, it means you fail. Okay. When the unit load is between 0 and 6. Okay. So that means your MD is equal to RA multiplied by 6 plus RB multiplied by 3. And now this distance is x. So here is 6 minus x, right? So that is minus 1, 6 minus x. That's your moment equation. And when the unit load is between 6 and 9, you have this free body diagram, which is without the unit load. because the unit load moved past this free body diagram already. So your MD is now RA multiplied by 6 minus RB multiplied by 3. Okay. Now, you may think that actually, when you look at this, can I use the free body diagram of MD on the right side? What do you think? If I don't want to involve the unit load, and can I use this? What do you think? Of course you can, right? When you cut the free body diagram at D to try to obtain MD, whether you use the free body diagram on the left or whether you use it on the right, the one on the right, you should get the same answer. Otherwise, you don't have equilibrium, correct? But let's just make sure that you use the correct value to get it, okay? I haven't fixed this number. The number needs fixing. You want us to do together, or you can do it later yourself. Okay.
Let's do it together.
Oh, sure. Good. You're always active, you know. And the good thing is you make me active as well. I kind of like that. But let me try to. Okay. That's our free body diagram. So we're going to have to do this. It means that I need to do something like this. Let's see. Let's try to be consistent. Okay. When the unit load is at 1, what's involved? RA is how much? 0.593, right? RB is the actually no, that's RB. Okay. Right. It's pretty tricky. RA is 0.437. Okay. And just maybe to make our life a little easier, should put X in here as well. X is 1.5, correct? When it is at point B, A is 0, B is 1, X is 3. When it is at point 2, A is minus 0.22, B is 1.08. Our distance becomes 4.5. At point C, sorry, that at point D, right? C, at point D, RA is minus a quarter. B is 0.875, X is 6. And at point 3, maybe you want to do something, because here is when we change the equation, right? You can use both equation and you're supposed to get the same MD, I suppose. So let's put another line here so that we can recognize that. And at 3, RA is minus 0.156. B is 0.484, am I right? Here is 7. Okay, now you do the job. My calculator on the telephone is not advanced enough, because you can write one equation, right, and just keep plugging the number away. But for those of you, you should try to do it together. But let me tell you that, because again, we can use Muller-Breslau to try to we can use Muller-Breslau to try to approximate the shape. Okay, you free this and you apply the moment here, and because this is a simple structure, it should go up like that. Okay. Oh, how come it takes so long, man? Anyone? I know at point B here must be 0, so at least I got 1. You like that? Ah. Come on, come on.
Okay, the first one is negative 0.096.
0.96. So what about others? You got the same number?
I got negative 0.099.
That's great. We can say it's 0.01, right? So let's say it's okay. So let's move on to this and then that. Thanks for your participation, everyone.
0.42.
0.42. What about you, Nakarin? Pretty similar?
Same.
Okay, great. Now at D should be a big value.
One 1.125.
1.125. What about you, Akrapan? Pretty similar, maybe?
Fit that. Maybe you can go other and I will recheck this because I deleted all. Sorry.
Oh, why? Anyway, the last point. Maybe it's a straight line here because, if you put a hinge there, this shouldn't be a curve, right? And a half.
Yeah, I got the same.
Same. I'm just looking for this now. Okay, but yeah, it's confirmed that it's a 1.5 Wow, just look at the sun outside. Looks to be another hot day.
And the negative 2.388 for the last one.
2.3.
Negative 2.3.
It has to be. It can be 2. It has to be less than 1. Let's look at the shape. Here's the value. Can be negative as well. You got the wrong equation. Maybe you have to change equation to this one, huh?
Right. I changed this.
Really?
Right. I checked this.
Oh, you know what? It's positive here. This is my bad. That can be negative. Right. So maybe change one more time. Sorry, my fault.
0.516.
See, that's engineering sense. 0.516. So that's confirmed that it's a straight line. It's a curve. Okay. So that's how we do it. Okay. Actually, we can end the class here, but I have another example just to see, to get you more example, because I don't have any intention to go beyond 1 degree of redundancy. So you either have the beam with 3 supports or a prop cantilever like this. You need to learn and understand. Okay. And again, let's say if you are given the information about the displacement, the rest should be really escape, right? So for me, it's best to use RC as a redundant. Okay, so I'm going to give you the information. So let's say delta 1 here is minus 6. Because it's exact number. So let me. Okay. Actually, it's 0.1875 over EI. Delta B is minus 22.5 over EI. Delta 2 is minus 45. Same line. Minus 45.5625. Okay. And then delta C here is minus 72 over EI. Delta D becomes a straight line, right? Is minus 99 over EI. So similarly, say if this is the given information about this, okay. This is the information. You must know that you can use this to solve for RC, okay? So we can go ahead and do the influence line of RC. So it's going to be, you know, the minus sign indicates that it should go upward. Straight line. This part, you know, when you apply the load like this particular point, this is a straight line, right? This portion is a straight line, and therefore your influence line, maybe I should move it down. Your influence line should look something like this. And then this a straight line. Okay. And now you know the value here. This is how should I write that? So let you know, I want to be consistent, so I'm just going to go back up and see how I write. Yeah, okay. So yeah, it's long one. I better do the same so that you get the better picture. RC when the is at 1. So that's going to be everything is divided by displacement at C, right? So that is 6.188 over 72, right? That is roughly very less 0.86 when one is at point B. The RC is equal to 22.5 divided by 72. Okay, so that is 0.3125 actually. And that is at 0.2 here. One is at 2, so that becomes 45.56 over 72. And that is 0.633. This point is, you know, no need to do it, right? It's 1. Okay, and then at point D is 99 over 72. But remember that this is a straight line, and that is 1.375. So that's it. You know, once you are given the information like this, whether in terms of the numbers right away or whether in terms of formula, you should be able to handle it. Okay, see, it's easy. Once you crack the code, okay, just need to know how to turn this information into the first inference line, because now you know the rest is just say MA, we get RC already. So next in line should be MA. Okay. So for MA, okay. Now remember you have this structure. But this time, you know RC, right? I kind of prefer, this is my preference, you know, for a continuous beam with 3 supports, I prefer to remove the one in the middle. And for a prop cantilever like this, I kind of prefer to remove this reaction. Okay, so that's what you have. And you can use this to write your equation. And this, because MA is that, so we have just one equation now. MA is equal to RC multiplied by 6, right? Minus 1. This is a unit load. We take moment a day, right? Take the moment here, so at 1 multiply by X. Okay, because that's the X. Use that, you get the inference line. It's going to look like this. And you can guess that, you know, when you apply the unit load like that, you should have negative moment, right? Until here, where it moves past point C, that's when you're going to have the positive moment. Again, that should be a straight line. Okay. And let me give you the number. Maybe you can work and see if I'm correct. That is minus 9. Sorry, minus 0.984 minus 1.125 minus 0.702. And that is 0.75. Okay, and that is this equation. Okay. Now, next is RA, right? For RA, now it's pretty simple because you know RC. You can just use sigma Fy equal to 0, right? So RA basically is 1 minus RC, right? Pretty simple. Okay. So too far away. And you have something like this. Because RC is like that, so RA should be something like this. Oops. And then this again, a straight line. Okay, this should be straightforward enough because you know, that's your equation, right? So that's going to be 1. It's a curve, even though this equation looks kind of innocuous because you know your RC is a curve, right? So maybe I should move this away a little bit. Okay, and here is 914, 6875. And here is 0.367. Okay. 4 minus 0.37. Okay, straightforward enough. Now here comes the tricky part where, you know, I always ask for this. MC, right? You know, when you look at the structure, if you still understand what the influence line is all about, you cannot have moment at C. MC only occurs when your unit load is, you know, from C to D, right? Because when your unit load is here, how can you have moment at that location? You have to put the unit load here so that you have moment. So this guy has nothing to do with the previous calculation at all. And you have this, right? And when you put the unit load here, because that distance is 1.5, so that becomes minus 1.5. Simple as that. Right? It's just like a test whether or not you know the behavior of the structure, rather. But when the next one is VB, this is MC. VB is again as usual. Okay. You can have this free body diagram. Where's point B? Okay. Okay. Then you have that. Right. So you can just use this free body diagram, you know. So I will have this. Then I have VB. Then I have my unit load. Okay. This is it means that my shear at B is equal to RA minus 1, right? This is when X is from 0 to the location of B, which is 3. And the next, when the unit load moves away from this, your free body diagram is simply without the unit load, which makes your life very easy now. This is when your, let's say this, okay? Oops, sorry. 3x and 7.5, right? your VB is simply RA. Okay. From that, you're gonna get the influence line looks like this. The 1, 2, 3. The second part is basically the opposite of RA, right? You flip that. That's RA. Oh, sorry. It's going to be a curve. That portion is RA. Pretty similar to that, okay? From B onward. The rest is just RA and -1, okay? So here is essentially RA. So I'm not going to give you all the ordinates, okay? So straightforward. That's 0.86 and then minus 0.3125. Not giving you the ordinates here actually should give you a better idea that this is basically RA. And then the last one is MB. Again, from this I can use this, you know, from pretty much the same, this guy. Now I can write another free body diagram. Okay. MB this time, the first one with the unit load on it. Okay. So basically this is when the unit load is from 0 to 3. Now your MB is equal to minus MA plus RA multiplied by 3. Of course, we take moment B minus the unit load multiplied by 3 minus X. Okay. And the second is, of course, this free body, same free body, but without the unit load. This is applicable when the unit load is from 3 to 7.5. And MB is equal to minus MA plus RA by 3. Pretty straightforward. So, you know, the trick is just with how you turn deformation into the solution of the first redundant, and the rest is just playing around with free body diagram and equilibrium. It's just like, you know, games. Okay. And from here we have the influence line, and it's going to look like this. 2, 3, 4, 5. So this is what your MB is going to look like. Try to do better job. Okay. And this is 0.258. This is 0.938. 0.4 minus 0.375. Okay, this is this, and this is that. Okay, so that's it. If you understand both patterns, you should be fine. Okay, and if you guys working on this, because I want to share something on the computer. Hello.
Yes. I can hear.
Can I stop this sharing because I want to show you some file.
For me, yes.
Okay. So I think no objection. So let's share another one here. Okay. All right. So generally, you know, here the first example, you see that the deformation is given just like that. So you need to know how to turn this given information into the reaction. Okay. And look at the first. Can I have the one moment. Okay. Here you know the situation that your load P is given like this, right? So this information of displacement is based on this load P. So this information is based on this. So you must know that you have to turn this into the deformation, and because it's given here, so it's deformation at E to obtain RE. Okay. Oops. Yeah, right. It just doesn't go with you. Okay. And for this, now it's been given in terms of the formula instead. So you need to know how to make use of the formulas to turn this into, you know, deformation like that. Okay. Here, so from information regarding displacement at any x point of an overhanging beam, okay, at any x point, deformation at any x point, I give the deflected shape. So you must know that if you want to calculate deflection between the two supports, you need to use the first one, and the second formula is for, you know, x1. See, x1. This is like, you know, use the given information. So the first formula will give you the deformation between the supports, and the second one gives you the deformation beyond the roller. Right? Give this, that. What does this imply? You must understand that this would imply the fact that, you know, you can use this to calculate the here maybe RC instead of the one in the middle. Okay, for example, that's the key. All right, and this is the active session number 6, and let's say, you know, we'll see about that because last time there was nobody. Okay, so is there any question? You want me to go back to the lecture maybe? Hello. That's it. The end of the semester. And we one more homework about the influence line.
I have a question.
Yeah.
Could you back to the lecture, please?
Okay, I will.
Sure.
Let's hope that we succeed. I can install one. How can you call it? It's an installation. Once that you know, once you have to keep installing the thing. Joke. Okay, we're back. Okay.
I have a question for the first example at the last part.
The first
Yes, last part
yeah.
for event line. Yeah, this one. I just wonder that why the location of when we consider MD, right? Why it will be greater than 1 since we're gonna apply the unit. Moment.
What do you mean?
You understand?
I'm afraid I don't. Can you repeat the question?
Okay, sure. If the influence line that we're gonna consider. For example, non-vector shear or the moment, right? At the location that we're gonna consider, this one will be only one, right? Because it's a unit. For example,
Yes, because we construct the influence line by using the unit load.
yeah. But why it will become 1.125? Just want to know, like, why not
Here,
become
that's a
one?
moment. You have to calculate the moment, not the load. This is the value. I mean, this,
Yes.
that's a value of moment from either one of these equations.
Oh, okay, I see. It's not unit. Okay.
Okay. So it happens like all the time, you know, because the most one of the most important part of the influence line is to change your perspective from either shear force or bending moment diagram into the influence line itself. Okay, this is moment. So you need to calculate moment. It has nothing to do with the load directly. It has a relationship, but it's not direct. You have to have moment. Okay.
All right. Okay.
So is there any more question? Maybe I should pause the record first.